Imagine a place so violent that space and time themselves warp. At the center of our galaxy lies a supermassive black hole with a gravitational pull so immense it anchors millions of stars in a tight, chaotic swarm. It's a neighborhood dominated by intense radiation, blistering stellar winds, and gravitational stress extreme enough to shred anything fragile that wanders too close. Conventionally, astronomers believed that any delicate, complex molecule, water included, would be instantly torn apart here. No exceptions. But in August 2026, the James Webb Space Telescope looked into the heart of that cosmic wasteland and found something that, by every rule astronomers thought they understood, shouldn't exist. Just 0.55 light years from the edge of the abyss, a distance so close it's practically in the black hole's front yard, a massive dying star is actively shedding water and dust directly into that hostile environment. And somehow, that water is surviving. How is a dying star still shedding water and dust in one of the most hostile environments in the galaxy? How does something as delicate as a molecule of H2O survive right next to a supermassive black hole? This is AI Investigates, and today we're going inside the data on a discovery that has quietly rewritten what scientists thought they knew about cosmic chemistry. Astronomers have a term for the region immediately surrounding a supermassive black hole: the sphere of influence, the zone where its gravity dominates everything else nearby. Get anywhere close to that zone, and the environment stops behaving like the rest of the galaxy. Radiation levels spike, gravitational stress builds, and, according to decades of assumptions, chemistry as we know it simply stops working. That's exactly the zone this star calls home. To understand why this shocked the scientific community, you first have to understand exactly what this star is up against. At the center of the Milky Way sits Sagittarius A, or SGA house for short, the supermassive black hole anchoring our entire galaxy. It sits about 26,000 light-years from Earth, and its gravity is so overwhelming that it dictates the orbits of everything for trillions of miles around it. The environment surrounding SGRA is not calm. It's a chaotic, high-energy tempest. Gas and dust spiraling toward the black hole heat up to extreme temperatures and blast out heavy doses of ultraviolet and X-ray radiation, the same kind of radiation that damages living cells in small doses, except magnified across a region packed with hundreds of massive young stars, all pumping out more of it. For decades, the consensus among astrophysicists was simple: that radiation acts as a hard barrier to complex chemistry. Nothing delicate survives long enough to matter. Water and other complex molecules are notoriously fragile. Expose them to intense stellar radiation, or the energetic outbursts flaring off a black hole's edge, and their chemical bonds come apart the way a house of cards collapses the second somebody bumps the table. Scientists assumed this region was a zone of absolute sterilization, a place where the basic ingredients that eventually build planets, and maybe even life, could never survive long enough to matter. But right in the middle of that hostile, irradiated territory sits a star that appears to break every one of those rules. It's called IRS-3, and it's located just 0.55 light-years, or 0.17 parsecs, to use the measurement astronomers actually work in, from Sagittarius A. In astronomical terms, that is not a distant neighbor. That is next door. This object is the brightest compact mid-infrared source anywhere in the central light year of our galaxy. For years, astronomers have watched IRS-3 with a mix of fascination and confusion. It's a highly evolved giant star, heavily wrapped in an enormous envelope of gas and dust, the kind of shroud that forms naturally around a star late in its life. But its very presence here defies expectations. How does a star, let alone a delicate cloud of dust surrounding it, manage to form and survive this close to the galaxy's central supermassive black hole without being torn apart or stripped completely bare? Before Webb turned its focus to IRS-3, scientists had already been trying to decode its secrets for over 2 decades, and every earlier look only deepened the mystery. Back in 2005, a study using the Very Large Telescope Interferometer, or VLTI, an array of telescopes in Chile that combine their light to see finer detail than any single telescope could manage alone, partially resolved the star's compact dust envelope for the first time. Then, in 2017, a team using the Very Large Array and ALMA, two of the most powerful radio observatories on Earth, detected radio and millimeter emission from the star. They found that IRS-3's envelope was being visibly influenced by SGR-A's gravity, showing clear signs of tidal distortion, meaning the black hole's pull was physically stretching and reshaping the cloud of material around the star. In fact, the high-resolution images revealed that the outer shell of dust appeared to be breaking up into fingers, thin streams pointing directly toward the black hole, like smoke being pulled toward an open window. Yet, because ground-based telescopes have their limits, even from some of the best observatories on the planet, scientists had to make a critical assumption to fill in the gaps. Based on the size and brightness of its dust envelope, they assumed IRS-3 was a carbon-rich star, one of the more common types of aging giants. But as is often the case in astrophysics, a closer look would soon turn that long-held assumption completely upside down. In 2025, astronomers launched the MICONIC program, a guaranteed time observations initiative aimed at characterizing the centers of nearby iconic galaxies using the James Webb Space Telescope. Guaranteed time simply means these are observing hours reserved in advance for scientists who helped build Webb's instruments, time set aside specifically to point the telescope at the most scientifically valuable targets in the sky. The Milky Way's own galactic center made that list. Led by Macarena Garcia Marin of the European Space Agency, the team pointed Webb's mid-infrared instrument, known as MIRI, directly at IRS-3. MIRI's medium-resolution spectrometer did something that had never been done before at this star. It captured a continuous, unbroken mid-infrared spectrum, essentially a complete chemical readout of the light coming off IRS-3 and its dust, with no gaps for anything to hide in. When the data was processed and accepted for publication in the journal Astronomy and Astrophysics in August 2026, it revealed a spectral fingerprint that was almost nothing like what scientists had predicted. The first shock came when researchers analyzed that spectrum to identify what the dust around IRS-3 was actually made of. Instead of the carbon-rich features they expected, the data revealed two unmistakable absorption signatures. Dips in the spectrum produced exclusively by silicate dust, material built from silicon and oxygen rather than carbon. Webb also picked up signatures of alumina, or aluminum oxide, close to the star itself. That chemical signature was definitive. The old assumption was dead. IRS-3 wasn't a carbon star at all. It was an oxygen-rich evolved star nearing the end of its life, one that was actively enriching one of the most extreme environments in the galaxy with freshly formed silicate grains, seeding the region with raw material it had never been credited with producing. But the dust wasn't the biggest surprise. That was still buried deeper in the data. Hidden within that continuous mid-infrared spectrum, the MIRI instrument detected a signature astronomers never expected to find in this harsh neighborhood: the clear, unambiguous chemical fingerprint of water molecules. To be completely clear, this water was not found inside the black hole itself, and it was never anywhere near the black hole's event horizon. It was discovered within the protective dusty envelope of the dying star IRS-3, which orbits just over half a light-year away from Esquerres. That distinction matters. This is the first time water has ever been detected in the envelope of IRS-3. And it's proof that one of the most fundamental molecular building blocks in the universe can survive surprisingly close to a supermassive black hole, as long as it has the right kind of shelter. So, how is this possible? How does water avoid being instantly torn apart by the intense ultraviolet and X-ray radiation pouring out of Esquerres' neighborhood? The answer lies in the physics of IRS-3's dusty envelope. To understand its structure, the research team ran complex computer simulations, testing roughly 100,000 variations of radiation transport models, essentially digital experiments that track how radiation and heat move through a cloud of dust, until they found the version that matched what Webb actually observed. The models revealed that IRS-3 is wrapped in a massive, layered, shell-like envelope of dust, extending roughly 10,000 astronomical units into space. One astronomical unit is the distance from the Earth to the Sun. So this envelope stretches to a scale that dwarfs our entire solar system many times over. That envelope acts as a physical shield, and it isn't uniform. Close to the star, where temperatures hover around 1200 Kelvin, roughly 1700 degrees Fahrenheit, hot aluminum oxide dominates. But moving outward, the temperature drops by a gradient of nearly 1000 Kelvin, plummeting to a freezing 100 Kelvin, about 280 degrees below 0 Fahrenheit, in the envelope's outer regions. That vast, dense cocoon of dust and gas absorbs the lethal radiation pouring off the region near the black hole before it can ever reach the envelope's protected interior, creating a safe, insulated microenvironment deep inside where delicate water molecules can survive fully intact. Think of it less like an open umbrella and more like a bunker with 10,000 feet of concrete stacked between the surface and whatever's sheltering inside. But IRS-3 cannot protect this water forever, because the star itself is running out of time. Webb's stellar modelling confirms that IRS-3 is roughly 6 times the mass of our Sun, with an estimated age of 72 million years, young by stellar standards but already near the end of its road. It has entered its asymptotic giant branch phase, the final chapter of a star's life before it sheds its outer layers for good. At this stage, the star has ballooned dramatically in size, cooled down, and is glowing with a luminosity about 60,000 times that of our Sun. Because it's dying, IRS-3 is undergoing intense mass loss, violently ejecting its outer layers into space through powerful stellar winds. The very envelope that's shielding that water right now is, in a very real sense, the star's dying breath, cast off into the void and destined to keep expanding and thinning until, eventually, the protection runs out. Which brings us to the most profound implication of the entire investigation. If a dying star like IRS-3 can keep forging silicate dust and shielding water molecules in the single most hostile, radiation-dominated environment in the entire Milky Way, then dust production and the chemistry that depends on it is far more resilient than scientists ever gave it credit for. Evolved stars don't stop contributing to their surroundings just because they happen to be sitting on the doorstep of a supermassive black hole. They keep recycling their elements, seeding even the galaxy's most violent neighborhood with the building blocks of future planets, future dust clouds, future generations of stars. Every rocky planet, every ocean, every molecule of water anywhere in the universe ultimately traces back to a dying star doing exactly what IRS-3 is doing right now, shedding its material back into space for something else to use later. Finding that process still running this close to a supermassive black hole means the raw ingredients for future worlds may be seeding themselves in places astronomers had written off as far too hostile to matter. Sagittarius A may rule the center of our galaxy with a gravity nothing else can match. But right in its shadow, a dying star has quietly proven that the chemistry of the universe finds a way to survive, even in the one place scientists were certain it couldn't. Thanks for watching this one all the way through. If you learned something new about what's really happening at the center of our galaxy, do us a favor and hit like. It genuinely helps more people find this channel. Subscribe if you want more deep dives like this one into the science stories that don't get the headlines they deserve. And drop a comment with a topic you want us to investigate next. A good chunk of what we cover here started as a suggestion right down there. We'll see you in the next one.